Welcome to solverfy.
This is the answer to Chapter 19, problem number 49 from the Smith Organic Chemistry textbook. And this problem says, draw all resonance structures of the conjugate bases formed by removal of the labeled protons A, B, and C in 1,3-cyclohexane dione and acetanilide. For each compound, rank those protons in order of increasing acidity and explain the order you chose. All right, so starting with 1,3-cyclohexane dione, we will just go in order. So the loss of proton HA is going to give us this molecule. With a lone pair and a negative charge there. And then there's one resonance structure that we can draw. That's going to be a result of the lone pair going there and these electrons kicking up to the oxygen. And so we can potentially have our double bond there, single bond there, 3 lone pairs and the negative charge on this oxygen now. So just like that. All right. As far as HB, so this was HA being lost. As far as HB being lost, there's really only one structure we can draw. So if we were to have HB be snatched off, we would get this structure where the lone pair and the negative charge are on the carbon that HB was on. And there's not really anywhere for those electrons to go. So that's it. That's the only structure there, no resonance structures. Which brings us to the loss of HC. So, okay, so if HC were to be the proton that got plucked off, we would have the lone pair there, the negative charge there. And we can delocalize that. So the electrons can either go here, and this double bond can break, and those electrons can revert to that oxygen, or they can go the other way, and those electrons can revert to that oxygen. So we have 2 possible resonance structures here. They look like this. So possible, oh, sorry, that's not right. So potentially this one with a double bond there, or if we were to follow the red arrows, we would get this where the double bond is here, and this is a single bond, and this double bond is still intact. So let me put my my lone pairs and charges in. So if we follow the blue arrows, we get to that. And if we follow the red arrows, then the extra lone pair and the negative charge is there. Okay, and so those are our 3 resonance structures for HC. So in order of increasing acidity, remember that the more stable conjugate base is going to have the more acidic acid. And so number of resonance structures correlates directly with stability. So HB only has 1 resonance structure. So HB is going to be the least stable base and therefore the weakest acid. HA has 2 resonance structures, so therefore it's going to be intermediate in terms of conjugate base stability and therefore acidity. And HC with 3 resonance structures is going to be the most acidic. So then we just need to do the exact same thing for acetanilide here in terms of A, B, and C. Unfortunately for B, there are 7 potential resonance structures. So this is going to take me a couple minutes to draw when we get to that point. But let's start with A. So if we lose A, that's going to result in this molecule. So 3. So that's going to look like this with the lone pair and the negative charge on this carbon. And there's really nowhere for that to go. There's no potential resonance structures there. So this is HA here, and this only has one resonance structure. So we should know from the previous problem that's probably going to be our weakest conjugate base and our least stable acid. So I'm going to skip B for right now and do C because C is much easier than B. So if we were to lose proton B, so this is HB that we're talking about now. So if we were to lose HB, we would, I just said I'm going to skip B and do C instead. Then I started to draw B. Okay, so let's talk about HC first. And I mean it this time. So if we were to lose HC, we would get our lone pair and our negative charge there on this carbon. And there is one potential resonance structure that we can draw here. So these electrons can add in here to make a carbon-carbon double bond. These electrons can revert to this oxygen. And so we have the resonance structure that looks like this. So double bond there, single bond to this oxygen, and the oxygen is going to be the seat of our negative charge. And so now let's do HB. So I'm going to put this on its own page because there are going to be, as I said, 7 resonance structures here. So it's quite a bit. So N. So here is deprotonated HB. So the nitrogen now has 2 lone pairs and it has a negative charge. And so the first resonance structure that we can draw is going to look like this. So one of these lone pairs can add in here. This double bond, one of the bonds can break and those electrons can revert to the oxygen. And that will give us, that will give us this. With 1 lone pair on the nitrogen now and 3 lone pairs and a negative charge on this oxygen. We can conceive of another resonance structure here, very similar, where the electrons of these double bonds just move around this aromatic ring. So nothing really changes, but it is technically a resonance structure here. Okay, so there we go. Okay, and so we could also, and I'll use red to show what I mean. So instead of that sort of sequence, if instead the lone pair of electrons on the nitrogen added in the other way, we could do that and have that double bond break. And so if we follow the red arrows here, what we get is this. And so now we have a lone pair and a negative charge on this carbon. And from here, we're basically just going to move these electrons around this ring. So they'll add in here. These will go here. These will go here. It's going to give us this. So our lone pair and negative charge are here now. Oh, wait. Oh, so that's what I did. I drew too many arrows at once. So rather than do that, okay. So these electrons should be going to this carbon. And that other double bond is going to be unaffected. So this is what we would get for this resonance structure. So now from here, now these electrons could add in here, and these electrons could revert to that carbon. Okay, there we go. All right, so there's our lone pair and our negative charge. Put our other lone pairs in. Okay, and so from here now, these electrons can go here. These electrons can go here. And now we've sort of gotten back to where we started, but the bonds in the aromatic ring are in different places. So if you compare where they were at the beginning to where they are now, it's different. One, two, 1, 2. The nitrogen has two lone pairs and the positive. Not a positive charge. Oh boy. So the nitrogen has two lone pairs and a negative charge once again. But as I said, the bonds are different around the aromatic ring. And so this is all of this is the potential resonance structures if we remove HB. And so going back to this part of the question, so HA has one resonance structure. So it's going to be the least stable conjugate base and therefore the least acidic acid. HC has two resonance structures. So it's going to be intermediately stable. And so the intermediate acid. And HB, when it's removed, there are 7 potential resonance structures for its conjugate base. And so it's going to be the most stable conjugate base and therefore the strongest acid. And let me just make sure. Yeah, and so that's everything that we were asked in this question. Yeah, so a lot of resonance structures to draw here. But when you do draw them all out, these answers do make sense. And it is good practice always to draw resonance structures. As you saw, I messed it up a little bit at one part. Yeah, so it's always good to practice. And that's the answer to chapter 19, problem number 49.